What's up, AP Pre-Calculus students? Mr. Mester coming at you. Unit 6, about trigonometry. Okay? Completely different from stuff we did in Algebra 2. We're going back to kind of geometry days. And we're going to go back and look at our triangles from geometry. The Greeks discovered, not really discovered, and they probably weren't the ones who discovered it, but they understood how triangles of different sizes, they had the same angle measurements. They had similar shapes where the lengths of their sides were proportional. And they created these functions to utilize that when they were doing buildings and anything involving lengths. You could turn it into like a triangle with a y distance, an x distance, and a diagonal distance. And if you understood ratios that you're supposed to have for certain angles that you have, boom, you know how tall or long or diagonally how long you need lengths to be able to build stuff and to figure out really any kind of distance just by using the right triangle. And we started with just these simple trig functions: sine, cosine, and tangent. Sine of an angle is equal to the ratio of the opposite side of the hypotenuse for any triangle with this particular angle. Now, I don't know what this angle measurement is, but this is a very specific angle measurement for a 3, 4, 5 right triangle. And for whatever this angle measurement, this is again like a very specific one. This is just in general. For this specific angle measurement that occurs in a 3, 4, 5 right triangle, the sine always has to be 3/5. Okay. That means like if you wanted a hypotenuse length of 10, well, this would have to be 6. You'd have to double the side length so that you had this ratio of 6 divided by 10 equivalent to 3 divided by 5. Okay, moving on, being less long-winded. Cosine is equal to the adjacent side with respect to the angle divided by the hypotenuse. If you're dealing with horizontals and diagonals, boom, you'd use this ratio for this specific angle measurement, 4/5. If you're talking about a height and a width, and you have this specific angle measurement, the tangent of this would be 3/4, and you'd use that ratio and you build. Cosecant, secant, cotangent are the reciprocal functions, which you have to remember cosecant being the same as 1 over sine. 1 over sine is just flip the fraction. 1 divided by 3/5 is the same as 1 times 5/3. Cosecant is sine flipped. So if you're kind of worried about the hypotenuse first, then the opposite, diagonal divided by the y, boom, you use that. Some situations it's more useful based on what you're accomplishing, what you're building, to use this reciprocal. So this is going to be 5/4. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Okay. We are going to switch gears towards very specific triangles that we are going to be using for the rest of the unit. And that is 30, 60, 90 triangles and 45, 45, 90 triangles. This is a tall oriented 30, 60, 90 triangle. This angle A is actually 60 degrees. It is the larger angle compared to this angle 30 degrees. Opposite the larger side, √3/2 is bigger than 1/2. This is something I want to get into your heads now because we will be using it in today's lesson and a lot more in the future. √3 is bigger than 1. √3 is like 1.7. So √3/2 is bigger than 1/2. Understand this is the longer leg. Obviously, it's not the longest side. 1 is going to be bigger than all of them. The hypotenuse is the longest side of a right triangle. But √3/2 is longer leg opposite the larger angle. Okay, so sine of A is really just asking what the sine of 60 degrees is. So this is the idea where it's like, I didn't know what this angle was. I could have looked it up actually really quickly. It's an inverse tangent of 3/4. 36.869 degrees. And you would have, we'll talk about inverse trig functions later. Just you could use an inverse trig function later in this homework. We talked about it in the notes. It's how you kind of just undo what's being done to an angle you might not know. So the sine of the specific angle, 36.869 degrees, is 3/5. And you could kind of see that the sine of that angle is 0.6, which is 3/5. Okay, so back to it. Sorry. The sine of this angle A, the sine of 60 degrees, is the opposite over the hypotenuse. Oh, great. I'm dividing by 1. Nothing changes. So I got √3/2 is the sine of 60 degrees, or the sine of A. The cosine of the angle A is 1/2 divided by 1. That's adjacent over hypotenuse. Well, that's just going to be 1/2. Ways to remember this, and I probably should have put it up, is SOHCAHTOA. But what's important is it's the trig function of an angle equals a ratio that needs to be consistent. This is an angle in a right triangle, and it's what mathematicians, Greeks, builders use to understand lengths when building. It's like, oh, you're using this angle, here's your ratio you have to have if you're talking about this length versus this length. Tangent of 60 degrees is opposite over adjacent. That's √3/2 divided by 1/2. Okay, here's our first instance of we don't like fractions over fractions. Besides dividing by 1 divided by 3/5, here would be something that might not be as obvious. Dividing by 1/2 is the same as multiplying by 2. Take 4 divided by 1/2, and you get 8. That's the same as 4 times 2. When you multiply this straight across, you could do 2 times √3/2. Just this is not √6. Don't make that mistake. Or you could just say, oh, divide the top and bottom of these fractions by 2, and you just get your answer √3. √3 is the ratio you need to have for an opposite over an adjacent for a 60-degree right triangle. Okay, now the other things we have to worry about is rationalizing. The cosecant would be the reciprocal of sine. Okay, move this over. Now, in this class, we are not allowed to divide by the square root of 3. Now, the reason behind this is because back in the day, we didn't have calculators. And if you wanted to take the number 2 and divide it by the square root of 3, you'd have to try to figure out what this was. A lot harder to do than if you were dividing a decimal, whatever the decimal might be, by a whole number 2 or by a whole number 3. This is easier to accomplish. So what mathematicians had to do to make calculations easier is they had to get rid of square roots in the bottom. Now, to do this, we're going to multiply the top and the bottom by the square root in the bottom. Why are we going to do that? Because the square root of 3 times the square root of 3 is just 3. It's like √3 squared, or √9. It's just 3. Don't worry. There's no plus or minus. We're not solving an equation. 2 times root 3 is 2 root 3. Mathematicians are a lot more easily able to take root 3, multiply it by 2, and then take 3 and divide that into to get a decimal approximation of what this is equivalent to. That's easier than that. So we like to, and we will ask you to rationalize, get rid of square roots in the bottom. Secant, though, easily done. Cotangent, not as easily done. Now, you could be able to kind of calculate this 2 different ways. You could have either said, well, cotangent's got to be adjacent over opposite. So adjacent would be the 1/2. The opposite would be the root 3 over 2. So this is 1/2 times 2 over root 3. You get 1 over root 3. Okay, well, that's like the same as taking root 3 and just flipping it. So probably, didn't want to show that, not necessary. But again, we want to rationalize. So again, it's harder to take 1 and divide it by root 3, but it's easier to take root 3. This is probably the best example to show this, and divide it by 3. That's a lot easier to do. So we would take 1 over root 3 and multiply it by root 3 over root 3, turns into root 3 over 3. Cool. So any triangle with a 60-degree angle, the ratio of the side lengths has to be these. Boom. If you want to build something, you want either this ratio, this is the angle that you have to be used. Oh, you want this angle to be used, this is the ratio of the side lengths that you have to have. Bam. Trigonometry helps understand lengths. All right. This, turns out, is a 45-degree angle. Okay? These are the basic side lengths of a 45, 45, 90 triangle. All of the side lengths have to have this kind of relationship where your legs have to be root 2 over 2, ends up being 1 over root 2. The hypotenuse has to be 1. We understand it's a isosceles triangle because it's a 45, 45, 90. If you remember from geometry, isosceles triangles, side lengths are the same. Angles have to be the same. So let's get into the ratios that we'll have to see if you ever have a 45, 45, 90 triangle. The sine, which is opposite over hypotenuse. And again, I'm just going to stick with this base angle. That way we don't get confused. Like the sine of 45 degrees has to be root 2 over 2. The sine of B is root 2 over 2. The cosine of this 45 degrees has to be root 2 over 2. Tangent has to be 1. I'm not going to do the math. Opposite divided by adjacent is something divided by itself. If you have a 45-degree triangle, the heights and the vertical lengths and the horizontal lengths will have to be the same. It has to be isosceles, no matter how big the triangle is. If we flipped 2 over root 2 and rationalized 2 root 2 over 2, oh, that's just going to be root 2. So secant's going to be root 2, and flip 1, you just get 1. Okay? You are responsible for knowing those special right triangles and the lengths. You are responsible for knowing and having memorized the 30, 60, 90 triangle and having memorized the 45, 45, 90 triangle. Okay? You are responsible for being able to draw it, no matter what the orientation is. So let's draw it. Now, we look at this first triangle, we realize 30 degrees, 90 degrees, this has to be 60 degrees. We have this kind of short 30, 60, 90 triangle. I'm going to be very exaggerated. We're going to say this is my smaller angle opposite my smaller side. This is my larger angle opposite my larger side. Now, we remember from the lesson and from the previous page that if the hypotenuse is 1, we got these two different side lengths, a smaller one and a larger one. This is important. This is how we're going to remember this. The smaller one is a half. We proved it in the lesson. The larger one is root 3 over 2 because root 3 is bigger than 1. So root 3 over 2 is bigger than 1 half. So this are the lengths of a 30, 60, 90 triangle with a hypotenuse of 1. Right triangles with 30, 60, 90 degrees will all have the same relationships, will have the same proportions of their side lengths. So they'll always follow the trig functions that we found earlier. Like these will have to be the ratios of their side lengths. Or we could say if this is x, this would be 1/2 x, and this would be root 3 over 2x. Or vice versa, any kind of variation of that we can use. So here, what if my hypotenuse was 8? Oh, okay, well, if this was 8, I would take 8 and multiply by half, and I get y has to be 4. I'd take 8 and multiply it by root 3 over 2, and I'd get 4 root 3. So this is how we can understand this proportionality of things. And then watch what's going to be great. Sine of 30 degrees, opposite over hypotenuse, 4 over 8. Oh, that's just going to be 1/2. If you went back up here, we did it with a 60-degree angle, but let's say we took this 30-degree angle, the sine would be 1/2 divided by 1. That's a half. We got the same ratio, 1/2. Of course, that's the whole idea of proportionality of triangles. So even though this is a bigger triangle, it's got to have proportional side lengths. That's trigonometry. Cosine, 4 root 3 is the adjacent side. 8 is the hypotenuse. Oh, root 3 over 2. Of course. Yeah, it's a 30, 60, 90 triangle. That's root 3 over 2, just like this root 3 over 2 would have to show up. Tangent of 30. Tangent is opposite over adjacent. It would be 4 over 4 root 3. Ends up being the same as the cotangent of 60. 1 over root 3 over 3. Cosecant is a reciprocal of sine. I found sine was a half, so cosecant is 2. These values will always show up when you're dealing with 30, 60, 90 triangles. These ratios will always show up. Here's another idea. 45, 45, 90 triangle. You are responsible for knowing that if you have a 45, 45, 90 triangle, you have an isosceles triangle. If the hypotenuse is 1, the legs would have to be root 2 over 2. Now, this is going to be the same deal where it's okay, if you change the hypotenuse, you can just multiply these side lengths by things. But here we have an idea where 4 is the leg length, and I don't know the hypotenuse. You could set up an equation. So 4 is equal to root 2 over 2 times x. Well, multiply or divide by root 2 over 2, you'd get, divide by root 2 over 2 is the same as multiplying by 2 over root 2. You'd get 8 over root 2, which is 8 root 2 over 2, which is 4 root 2. Okay, you know x has to be 4, and you just found out, I don't know, I should have just used something else besides x. Multiplier. My leg length, x has to be 4. It's isosceles. Okay, boom. What is my diagonal length? Okay, well, let's just find what our multiplier is. Root 2 over 2 times your multiplier is 4. That's going to have to be what the hypotenuse is, the multiplier. Multiplied by 2 over root 2 to solve. That's 8 over root 2, which is 8 root 2 over 2, which is 4 root 2. There's other ways to remind yourselves of like how, if you have a leg, how to find the hypotenuse. I mean, you could have also used the Pythagorean theorem. Double 4 squared has to equal y squared. 32 has to equal y squared. Y has to equal root 32, which is root 4 root 8. Just 2 root 8. Sorry, root 16 root 2. Root 16 root 2. 4 root 2. So, like, I didn't have to do it this way. I could have used the Pythagorean theorem. But 30, 60, 90s, it's not as easy to do the Pythagorean theorem because you won't have the same side length. So figuring things out no matter what. But it doesn't matter the size of your triangle. If your angles are 45, 45, 90, these ratios will appear. Root 2 over 2, 1, root 2. Those are the ratios that are going to appear. Here, sine. Opposite over hypotenuse. 4 over 4 root 2 is 1 over root 2 is root 2 over 2. Oh, we saw root 2 over 2 on the previous page for the sine of 45 degrees, root 2 over 2. The cosine of 45 degrees, cosine is 4 over 4 root 2, which is 1 over root 2, which is root 2 over 2. Oh, yeah, I kind of figured that out on the last page. The cosine of 45 degrees is root 2 over 2. Tangent's going to be 1. Secant is going to be just root 2. That's root 2 over 2 flipped. Boom, look at this triangle. That's 60 degrees. They're trying to trick you here. You should know what this is. If you remember, O, for a tall 30, 60, 90 triangle, and you have to have these memorized / known, the hypotenuse was 1, the tall side length is the longer leg length, root 3 over 2. The short is 1/2. The sine of 60 degrees is root 3 over 2. Has to be, no matter how large your triangle is. The ratios have to be consistent. Thank you, Greeks. The cosine of 60 degrees has to be 1/2. But let's try to get these values in a different way. Here, they're saying, well, what if the long side length was 1/2? Okay, well, I'm going to go back to kind of like this multiplier, this multiplier, this multiplier. If I just change all of the side lengths, we can kind of understand what this x and what this y is by looking at m. Okay, I'll start with 1/2 is equal to root 3 over 2 times this multiplier m. Let's find m by multiplying by 2 and dividing by root 3. I get 1 over root 3 is equal to m. So m is the same as root 3 over 3. So that's how we're going to find this hypotenuse length, which is just m times 1. The short length is m times 1/2. So that's got to be root 3 over 6. There are other ways to do this. I'm sure a lot of you have done it different ways, like if you're checking your answers. But this is how I like to do it. Cool. Now, what you'll find is if you did the sine of 60 degrees, this is your angle. The sine is opposite over hypotenuse. Opposite over hypotenuse. You'd have 1/2 times 2 over root 3, which is 1 over root 3. Hold on. 1/2 divided by root 3 over 3. We need to get an answer that we're looking for. The sine of 60 degrees is root 3 over 2. I'm just kind of using this to show you what we need to see. So I end up with 3 over 2 root 3. And you might be like, well, that's not the same, but like, let's rationalize. Multiply the top and bottom by root 3. I get 3 root 3 over 2 times 3. Oh, the 3's cancel. You get root 3 over 2 just like we expected it to get. It doesn't matter. The sides of our triangles, the ratios have to be the same because of the proportionality of these similar triangles. The cosine has to be a half. Do it with these side lengths. Root 3 over 6 is the adjacent side. The hypotenuse is root 3 over 3. That works out nicely. Or we don't have to rationalize because the root 3's cancel. 3 over 6 is 1 over 2. The tangent of 60 degrees is root 3. Okay. You want to get that a different way? 1/2 divided by root 3 over 6. Three over root 3. Rationalize. Many of you are thinking, like, Mr. Messer, do I have to do this? The answer is no. Like, no. Like, if you know the simplest version, the version with a hypotenuse of 1, you know all your trig functions. You know your ratios. You don't have to do this. Really, all you need is this, and that helps you find that and that. And the rest you should kind of know based on the easy one with the hypotenuse is 1. So what I'm doing is just showing you how it doesn't matter the size of your triangle. Proportionality exists. Cotangent, I already have tangent, so. Boom. All right, last one. Another 45, 45, 90. So I'm going to just go ahead and say, like, I'm going to skip all the extra work. Save you guys some time. You have to know the side lengths of root 2 over 2 if the hypotenuse is 1. This gives you the simplest version of this 45, 45, 90 triangle. The sine of 45 degrees, it doesn't matter where the 45 degrees is. It'll be same here or here, is root 2 over 2. The cosine is root 2 over 2. The tangent is 1, and the cosecant is root 2. Okay? Did not have to do the calculations with different values because we know they're going to be the same. But we do want to find these lengths. If this is a 45, 45, 90, and this is a hypotenuse of 12, that's your multiplier. Times 12. So m is 12. I need to take root 2 over 2 and multiply it by 12. This is 12 root 2 over 2. Divide the top and bottom by 2. 6 root 2. Do all of the work that we just did with 6 root 2, 6 root 2, and 12. You will get the same ratios as root 2 over 2, root 2 over 2. Cool. Now we get to, like, well, how could we find angles if we have lengths? Right now, we're not going to worry about why or how, and we're not going to get the value, but we just have to know that it exists. Let's look at this situation. I have x, this angle x, and I have the adjacent side and the hypotenuse. I probably should have done a better job on the first page, like making sure you understand, like, where's your angle, what is opposite, what is adjacent, what is hypotenuse. So I have an adjacent and a hypotenuse. In SOHCAHTOA, the trig function that deals with adjacents and hypotenuse is cosine. So remember, it's trig function of an angle gives you a consistent ratio no matter what size the triangle is. The cosine of this angle x will equal 9 over 12. Now, 9 over 12 can be simplified. That's not kind of the point of this, but let's just do it. 3/4. Now, we remember inverses from the last unit before the break. Inverses undo, map back to one another. The inverse for e to the x, the natural log x. The inverse for exponential functions, log functions. The inverse for x squared, square root x. Well, the inverse of f inverse. If I had f of x equals 3/4 and I said, hey, write an equation for x equals, you would use the inverse to get rid of f. So the whole idea of like flip-flop points, right? You'd say, well, x equals the inverse of f at 3/4. It's like mapping it back. Well, that's what we're going to kind of do here, is just understand that to undo cosine, use the inverse. We'll call it cos inverse. This is something that you could type into your calculator to get an angle measurement. Where does your calculator get those values from? Back in the day, people used to like look them up in tables and be like, oh, like go into the back of a textbook. We already have done like an analysis of all of these ratios for all of these different angles. Boom. You'd like look at 0.75 and find like the cosine inverse of it kind of deal. But no, we're just going to leave this answer like that and be okay with it. You can get an answer. It is a numerical answer, but right now we're just going to leave it to be comfortable with like, that's my angle, inverse cosine of 3/4. Cool. So here, if this is my angle, that's opposite. This is the hypotenuse. The sine deals with opposites and hypotenuses. The sine would be 9/12. Sine of the angle, trig function of an angle equals a ratio. The sine of x equals 3/4. Get rid of sine using sine inverse. And this is all we want you to do, just be comfortable with the existence of these inverse functions that can be used to find angle measurements if they're unknown. Okay? Same here, this is a sine because it's opposite and hypotenuse given. Can't simplify that, use sine inverse to solve for x. Use tangent, again, here's my angle. That's opposite, this is adjacent. Tangent is the trig function that deals with opposite over adjacent lengths. You'd use the inverse tangent to find an angle measurement if you had side lengths. The Greeks used to have like books where they did a bunch of calculations and kind of knew measurements and angles that went with those measurements. And they would like look them up in books. Mathematicians then discovered there's other stuff going on that can help you find those measurements or find the trig function of these angles without measuring, which you'll get into if you take calculus, and there's fun. This is very similar to the last one, and this is where we're going to end, where it's just like understanding this idea of trig function of an angle equals a ratio. Cool? Starting with that, and working with maybe inverses to find the angle or vice versa. We're going to write this in function notation. So B is the side length, A is the angle. F gives the values of B as a function of A. So write a formula for F of A. Okay, so F of A equals what? Well, I could start with understanding A is the angle, B is going to be the opposite side length, and 2 is going to be the hypotenuse. Using SOHCAHTOA, we understand that sine deals with opposites and hypotenuse. So I'd say that the sine of angle A equals B over 2. Okay. Well, I want to be able to plug in A and get an answer for B kind of deal. Where it's like plug in A, do some stuff with it, get an answer, get an output. What we want you to do is essentially just solve for B here, where you can say, okay, 2 times the sine of A has to equal B. Okay, take A, plug it into this machine, you'll get B. That's kind of the idea of like, it gives values of B as a function of A. 2 sine A equals B. Now, flipping things around, if we have an idea where I want to take B, do stuff to B to get A, this is where you would use the inverse sine of both sides to get that outputs of A will equal inverse sines of B over 2. This would be my formula for G of B, where your input values are B, and you're going to be mapping back to A's. What we have are inverses of each other. F and G are inverses of each other. 2 times the sine of A. To undo, you would take, to undo what's being done, you take your B, divide it by 2, and then the sine inverse of it. Take your B, divide it by 2, take the sine inverse. You essentially just found the inverses of the two functions for the specific triangle. Okay, so let's see if you got that. Do the other ones. Get plug in A, get B equals B. Plug in B, get A. See that they're inverses of each other, undoing each other. Here, A, angle, B is opposite. 4 is adjacent. So I'm going to use tangent. The tangent of A equals B over 4. Okay. Solving for B, I got 4 tangent A equals B. Solving for A, I get A equals tan inverse of B over 4. Let's say I plugged in A, took the tan of it, like found the ratio tangent of that angle, multiplied it by 4. Boom, you're outputting B. Take that B, map it back to A, divide it by 4, take the tan inverse of it. Boom. Inverses are what we're creating. So this one is our F of A that will output B. This one is our G of B, or F inverse of B, which will output A. Cool stuff. All right, this is adjacent to the angle A, and this is the hypotenuse. So I would get the cosine of A equals 1/2 over B. I'll keep it like that, but you could write it as 1 over 2B if you wanted to. Okay, let's solve for B. you would multiply by b and divide by cos A. So let's think about doing that. This would be your f of A. 1 over 2 cosine A. Plug that in, you get B. Multiply by B, divide by cos A. 1/2 divided by cos A can be written as well, but we don't want fractions inside of fractions. We prefer the other way around. Here, it is easy to just take the cos inverse of both sides. So it's like, take A, take the cosine of it, multiply by 2, divide that into 1. To flip that, you got a B, take your B, multiply that by 2, flip that back, take the cos inverse of it. I think that makes sense. Probably not. Okay. Last one. Here's A. This is adjacent to A. That would be opposite. This is the hypotenuse of A of this right triangle. Make sure you understand what the hypotenuse is and don't call this adjacent. This is the long side opposite the biggest angle. That's the hypotenuse. So it's another cosine. Cosine A equals 8 over B. Okay, so B equals 8 over cos A. A equals cos inverse of 8 over B. These are inverses of each other. F of A outputs B's. Take those B's, inverse, divide them into 8, and then inverse cosine. And boom, you'll pop back to A's. Cool. All right. Trigonometry, SOHCAHTOA, proportionality, super useful, super important, and it gets even more interesting moving forward. Looking forward to it. Sorry I wasn't in today, but if you're in my classes, you watched the intro video and understood why. Later.